Thank you. Yes, hi, I'm Carl. Great to be back at PyCon. Thank you for coming to the talk. So I'm one of the authors of TY, a Python type checker and language server from Astral, which as of 2 weeks ago is now part of OpenAI. So in this talk, we'll take a look under the hood at how TY works. So what is TY? It's a Python type checker. You can run it on your Python project. It will statically analyze the code and tell you if it detects any problems. So you run it on your code base, maybe locally, maybe in CI. For example, you run ty check, and it might say, all is well, no problems found. Or it might say, hey, you're trying to use a string where an integer is expected. Here's the bad call. Here's the definition of the function that you're calling. So that's one way you can use ty. Check your whole code base via the command line. ty is also a language server, which means you can set it up inside your editor or IDE via the VS Code extension, or the LSP features of your preferred editor. And then you can get TY's feedback directly as you type, with the red squiggly errors we all love, also lots more LSP features besides that. Auto-completions, of course, hover type information, function signature help, go to definition, go to declaration, find references, inlay hints, rename symbol, auto-import, auto-fixes, etc. And that, let's see, 2 minutes, 1.5 minutes, is all of the time that I want to spend in this talk on how to use TY. If you'd like to know more about usage and features, you can head on over to our docs and find a lot there. So let's get into the real topic of this talk. How does TY work? I'll try to cover 5 aspects of that here: laziness, control flow, the type system, diagnostics, and a final short section on contributing to TY. So one of our core requirements for TY is that it be fast. And of course, there are lots of ways that we work to make it fast. We care a lot about memory layout and access patterns. We use Rust so that we can control those things. We care about algorithmic efficiency. But by far the highest leverage way to be fast is to not do things that you don't need to do. So if the only use case we cared about for TY was to check your whole project start to finish, we might build it like a classic compiler as a linear sequence of phases on the entire project. First, find all the files, find everything they reference, then parse them all to a syntax tree, then translate to an IR. And that's not that far from what we do, but this approach is not very lazy. In the case of TY, we're a language server that wants to give updated feedback on every keystroke as you type. So you might be typing, making many small changes to a small set of files in what might be a very large code base. So TY is very fast, but on a very large code base, it might still take several seconds to recheck everything from scratch. And that's far longer than you want to wait in your editor after each keystroke. So TY is lazy. We do as little work as possible to give you the feedback you've requested, and incremental. When you make a change, we reuse as much as possible of our previous knowledge and recompute as little as possible. It also makes a difference at what granularity we're lazy and incremental. In a typical large Python code base, the module dependency graph tends to be highly tangled and cyclic. So if you change the 3 blue files here, the module level dependency graph would tell us that all of these yellow files need to be recomputed. So how can we avoid doing all this work? Let's look at 3 example files in more detail. Here, main imports inter, which imports core. So module level dependencies would say that main depends on inter, and inter depends on core. So obviously that means that if we're type checking main, we'll have to parse all 3 of these files, right? In fact, we can do better. If ty is asked to type check main, we'll see that it imports inter.c. We'll go evaluate just that visible binding of c, ignoring everything else in inter.py. We'll see that evaluating C requires A and B, so we'll evaluate them too, and that gives us everything we need. We'll never look at D at all, so we never look at core type, so we never even need to read the contents of core.py. And on the flip side, if we have checked all 3 of these modules, and then you make an edit to core.py, we'll recheck some parts of inter, and we won't need to recheck main at all. So the upshot of all this is that when you edit these 3 blue files, instead of rechecking all these files, we can just recheck parts of a much smaller set of files instead. So this helps us give really fast incremental updates in your editor as you type. But this fine-grained laziness actually can also make us much faster when we are doing a from-scratch check of your entire code base. So let's say that your project is relatively small. Maybe it consists of just these 3 files. But you have some dependencies. Maybe you depend on NumPy or SciPy, which are massive, much bigger than your project. So even if we check your whole project for errors, our fine-grained laziness means we can check only the minimal portion of your dependencies that your code actually uses and ignore all the stuff you don't use. And this can save a massive amount of time. So this kind of architecture is often called a query-based or on-demand architecture because we compute things only when we have to. So if you have just one file open in your IDE and you hover over the type of one variable, we can helicopter in right there and compute the minimum amount of things that we have to just to give you that single hover type. So of course, query-based architectures run headlong into one of the two hard problems in computer science, cache invalidation. If we're computing all these little granular bits of information on demand, we have to keep track of what we've already computed and what we haven't yet, so we avoid repeating work. And when you make a change, we then have to figure out which of all these cached bits of information are now out of date and have to be recomputed, and which ones remain valid and can just be reused. And it's easy to get this wrong and run into lots of annoying bugs where as you edit your code over time, the type checker results get out of sync and maybe don't match what you get on a fresh check. And that's a very frustrating experience. So in TY, we avoid this problem by using Salsa, which is not only delicious, but is also a Rust library for incremental computation. What does that mean? Salsa is built around the concept of a query. A query is really just a Rust function with some special behavior layered on top of it via macro. Here's an example. We have a function parsed module that takes a file, parses it, and returns an abstract syntax tree. So far, this is just a normal Rust function. To make it a Salsa query, we give it this Salsa tract attribute, and it also needs to accept the Salsa database as its first argument. With those changes, now this function is automatically memoized. If we call it on a file and then call it again on the same file, Salsa won't reparse the file or redo any work. It'll just hand us back the same AST from its cache that it calculated last time. And internally, Salsa is now automatically tracking a dependency graph. It knows that the cached result of parsed module for file 0 depends on the source text of file 0. The file source in this example is called a Salsa input. That means it doesn't depend on anything. It's a root node in the dependency graph. So Salsa will assume that it never changes unless we explicitly tell Salsa that it has changed. So in the TY LSP, we'll run a file watcher, and if we get an event telling us that a certain file has changed, we'll tell Salsa that it has changed. Since an input has changed, we're now in what Salsa calls a new revision, and so the next time we call parsed module, it'll reparse the file and generate a new AST for it. So now let's add another query, semantic index. This query also takes a file, and it calls our previous query, parsed module, to parse it into an AST. Salsa sees this call and automatically adds a new edge and node to our dependency graph. It sees that semantic index for a file depends on parsed module for that file. We won't worry quite yet about the details of what's in the semantic index or how we build it. We'll come back to that a bit later. So this is the core of how we manage laziness and incrementality in TY. We can write our logic as normal functions without worrying about caching, and we can freely call those functions as often as we want from wherever we want, knowing that Salsa will automatically ensure that repeat calls are cheap, and Salsa will take care of invalidation for us so we never have stale results. Okay, now let's dive into that semantic index step that we just mentioned and look at how we represent control flow in TY. So the purpose of the semantic index is to extract as much information as we can from a single Python file in isolation. And the reason for this, that this is important, is that it means that the semantic index for a given file doesn't have to be recomputed unless that file changes. There are no cross-cutting dependencies across your code base. The semantic index for a file just depends on that file's contents. So this obviously prevents a lot of invalidation of these. So in semantic indexing, we walk the AST of the file once, and we build up a tree of scopes in the file. So like the global scope, class scopes, function scopes, etc. For each scope, we build a symbol table, all the variables that we've seen. And then we build something called use-def chains for every use of a variable. The use-def chain represents our understanding of control flow, so let's look at that in more detail. Consider this function. It takes a Boolean flag, conditionally initializes a variable, x, and returns it. So as a type checker, one thing we need to do is to check whether the return x statement is valid. Does it always return an integer, as promised by the function's return annotation? So we can see looking at this that it doesn't, but for ty to see that, we need to know what values could x possibly have when we hit return x? Where might x have gotten its value? Or in other words, what bindings of x could be live when we hit return x in control flow? So in ty, we record this information in the semantic index for a file in a form called a use-def chain. That means that for every use of a variable, like in return x, we use the variable x, we will record a list of all the live bindings of x at that point in control flow. Then later in type inference, we can go look at each of those live bindings to understand what values x can possibly have at this spot. To build up these use-def chains, we walk the AST of the function and track the live bindings for each symbol. So for the live bindings of x here, at the start of the function, of course, there are none. X is not bound. After the first assignment, x equals none is our sole live binding. That means that if we used the variable x right here, we would know for sure that it got its value from the assignment x equals none and from nowhere else. When we hit the if branch, we make a note of the live bindings of x at this point. We'll need this later in order to model both branches. So then we visit the if branch, and the x equals 1 assignment replaces the previous live binding. So if we had a use of x inside this branch, we'd know that the only live binding of x is x equals 1 at this point. At the end of the if branch, the two possible control flow paths merge back together. There are two different ways we could reach the code after the if block. Either we took the branch or we didn't. If we took the branch, then x equals 1 is live. If we didn't take the branch, x equals none remains live. So we go back to the note we made earlier of the live bindings when entered the if branch, and we merge that into our live bindings from the branch. So now we have two live bindings. Both x equals none and x equals 1 are live. So we record these in our semantic index as the live bindings at the use of x in the return x statement. So one thing that's important to note here is that the things we are recording in semantic indexing are not types. We're not even working in the domain of types at all yet. What we record here is basically just a pointer to the AST node for the assignment. The reason for this is that resolving types often requires looking across file boundaries. You may have a type annotation or something, or you may assign an instance of a class to a variable, and that class is defined in some other file. So to have a type for that, we need to go look at that other file. And then you start having these dependencies all across your code base. And in semantic indexing, we want to record the information that we can get from one file in isolation. So all we're doing here is recording these pointers to the relevant AST nodes for later use in type inference. So later we can look at these two bindings we've recorded for return x, and then we can decide what the type of x will be in this statement. All right, so if we expand this example slightly, so we have an else branch that also assigns an integer to x. The first few steps here still look the same, but at the end of the if branch, we now need to also stash the live bindings from the if branch. Then we restore the live bindings from before the if branch, so that we can visit the else branch with the right state. And then at the end of the else branch, we merge the two states from the if branch and the else branch, and we end up with two live bindings, x equals 1 and x equals 2, and we record those for the return x in this case. The x equals none binding is no longer live because there's no possible control flow path where we can reach return x without it having been overwritten by either x equals 1 or x equals 2. Okay, one more example. Here, the initial binding of x in this scope comes from a function parameter. So we can't see the exact value bound to it. We know that a value will be bound to it, and we have a type annotation to describe that binding. So at the if branch, we notice that this if condition, if x is none, does impact the possible values of x. We call this a narrowing condition because it will allow us to infer a narrower type for x in each branch. So within the if branch, we know that our single live binding is also subject to an is none narrowing condition. At the end of the if branch, in this case, we don't merge the two control flow paths because the if branch is terminal. It returns, so it can't flow into the rest of the function. So instead, we just restore the live bindings for the case where the if branch was not taken, which remembers the inverse condition. X cannot be none. And then that's the state that we store for the use of X in return X. Again, we aren't resolving any types here. We don't say at this stage, oh, X was int or none, and now it can't be none, so it's just int. We're not doing any type evaluation at all. We're simply recording pointers to the relevant bindings and narrowing expressions for later evaluation. So this keeps the semantic index per file and means that one file changing only invalidates that file's semantic index. Okay, we have now covered enough of the basics that we can start talking about actual types soon. First, I'm going to revisit a bit of the Salsa architecture and start adding in some type inference queries to see how those look. So let's go back to these three files that we looked at earlier with the transitive dependency. And let's say, again, that we want to type check main.py. So ty will initially call the Salsa query check types on main.py, which will arbitrarily call file ID 2. What the check types query does is walk every scope in the file, type checking each one. So how do we get the scopes? Well, we have to get the semantic index for the file, which in turn has to parse the module, which has to read its source code. If we remember, this was actually quite a simple module, which only has one global scope. So check types calls the infer scope query on that global scope. This is not a typo. I've used 2G here sort of arbitrarily as the unique key for this scope. It's the global scope of file 2. That's not actually what the unique keys look like in Salsa, but just to give the idea that it has a unique key identifying that particular infer scope query. So when we check that scope, the global scope, in order to check the import statement, then we in turn call the infer binding query on the binding of C in the import statement, because that's where C is bound to a value in this scope. So at this point, we now have to go off to the module resolver, which is another entire subsystem, to figure out what file the inter module actually refers to. That involves calling more Salsa queries, which I'm eliding here. But once we've done that, we figure out that inter.py is the file we need to go to find the contents of the inter module. And then we have to get its semantic index in order to ask what bindings it has for the symbol C. And of course, that requires the parsed module and the source text for that file. So this module imports core and then defines some constants. But remember, we aren't checking this file. We're only checking main.py. So we're not actually running, infer scope in this file. All we need is to ask the semantic index for its bindings for C specifically. We find there's one binding, so we go infer its type. That means evaluating the right-hand side expression of that assignment, A plus B. In evaluating the type of that expression, we find uses of two other variables, A and B. So then we have to go ask the semantic index what the live bindings for A and B are, and of course they're right here. So we go infer types for those two bindings. And here we bottom out, because the right-hand sides of those two assignments are trivial. We can infer the types literal 1 and literal 2 for those without looking up any more bindings. Then we can go back and get the type for A plus B, and eventually we get to our type for C over in main.py. So because of our fine-grained laziness, we were able to do this without ever looking at the import of core at all, or even reading the source code of core.py. Okay, so now let's assume that we've now checked all three of these files in revision 1. So we've run all these queries. And now let's say we make a trivial edit to inter.py. We just update a comment maybe, or we reformat the file. So because a file changed, this immediately means that from Salsa's perspective, we're no longer in revision 1, we're in revision 2. Our file watcher has informed Salsa that inter.py has been modified. So now Salsa has cached values for all these queries from revision 1, but they're all in an unverified state in revision 2. We don't know yet whether they're still valid or not, given the change in revision 2. Salsa doesn't immediately go do anything about that. It just stays in that state and lazily waits for us to actually ask for something. So we ask once again to check main.py. Since we have this unverified cached information from revision 1, before Salsa runs any queries, it recursively validates whether any dependencies have changed. So we'll run up the main.py dependencies, and when we reach the file input, we find that this file input hasn't changed. we don't need to read the file, we don't have to even stat the file to determine this. Salsa just knows it because we haven't told Salsa that this file changed. So Salsa says, okay, my cached source text for this file is still valid in revision 2, and that means my cached AST and semantic index are also still valid. Great, so now we have to go down the other dependency path, through infer scope, to infer binding, and then over to the other module. So here we bottom out again at an input, but this one Salsa knows did change in revision 2. So we do have to re-execute the source text query to get the source of inter.py. And when we do, we find that the new source text is in fact different from the old one, so our cached value from revision 1 is invalidated. That means we also need to reparse the file, and we find that the new AST does differ from the old one. Even if the change we made is trivial, our AST does need to store exact source locations for all the AST nodes, because we need that later for emitting diagnostics. So even a trivial change is likely going to result in a different AST. So it's not really an AST, I guess, entirely. It's got some concrete details in it. Okay, so that means that we need to rerun semantic indexing for this file. But now something interesting happens. After we rerun semantic indexing, Salsa compares the new semantic index to the old one, and because we made only a trivial change to the file, the new semantic index is the same as the old one. Now, if you're paying careful attention, that might be a bit surprising, because I said earlier that the semantic index stores pointers into the AST, and we just said the AST changed. So how can the semantic index be unchanged? And that does require a little bit of cleverness. We use an AST node numbering system that assigns IDs to AST nodes, and it does that in a breadth-first way, which means that deeply nested changes tend to leave most of the IDs in the file stable. And the consequence of that is that the semantic index can store references to these node IDs, and those will often remain stable even in the face of some changes to the AST. And so the semantic index, for many changes, even if the AST changes, the semantic index may still be exactly the same. So now that we have an identical semantic index, that means that it's still valid in revision 2, and that means we're actually done. We don't have to rerun any of the rest of this. All of our cached values from revision 1 remain valid and reusable as is. So this is how we avoid doing unnecessary work, even when type inference dependencies cross module boundaries. So this algorithm, this incremental computation algorithm, is sometimes called the red-green algorithm for reasons I've made evident here. And now you also know how Salsa earned its name. So I promised that we would talk about types in this section of the talk, and somehow we're still talking about Salsa. So let's go back and look at this example. We looked at this earlier in semantic indexing, building the control flow, the use def chains. So now we're no longer in semantic indexing. We're doing type checking on this scope. And so we get to this return statement, and we want to check that this return statement is valid. So we want to know what the type of x is here in return x. So the first thing we do is we go ask the semantic index, what are the live bindings for this use of x? It'll tell us that these two assignments, x equals none and x equals 1. And then we call infer binding to get the type from each of those bindings. In this case, both are pretty trivial. The built-in none always has the type none, and a literal 1 has the type literal 1. So having two live bindings for x means that its value here could come from either binding. So it's an or. So that means the right type for x here is the union of the types from the two live bindings. So now checking this return is just a matter of asking whether that type is assignable to the annotated return type int. Of course it is not, since none is not a subtype of int, so we emit a type error on this return statement. Let's revisit one more of the control flow examples we looked at earlier. In this example, the type of x in return x has just one live binding, which gives us the type int or none, but it's also subject to a narrowing constraint from the if check, and that constraint contributes something new, a negation type. This type not none includes all Python objects other than none. In the previous example, we had two different bindings, and the value of x could come from either of them. That's an or, which maps to a union type. In this case, we have just one binding subject to an additional constraint. This is an and. The type of x here must be int or none, and it must be not none. This maps to a new kind of type, the dual of union, an intersection. So in TY type displays, we spell intersections with the ampersand and negations with the tilde, although this syntax isn't standardized at this point or supported at runtime. We should take a step back here and talk a little bit about what these intersection and negation types are, since we aren't used to seeing these in Python. The general term for union, intersection, and negation types is set-theoretic types, because these types map directly onto set theory. So let's do some Venn diagrams. Let's say this blob here represents all possible Python objects, every one in existence. We have a name for the type that includes all Python objects. It's object. If we have a class named A, then the type A includes all Python objects that are instances of A. Obviously, this is a subset of all Python objects, which means that A is a subtype of object, and object is a supertype of A. So what about the negation type, not A? Well, that's the set of all Python objects which are not instances of A. So it's all this negative space outside of A. If we have a second type B, now we can talk about unions and intersections. The union of A and B is the type representing all Python objects that are instances of A or instances of B, so it's the combined area of the A blob and the B blob. And then the intersection of A and B is the type representing all Python objects that are instances of A and instances of B, so it's the overlap between A and B. So if A and B are nominal types, that is classes, then their intersection would consist of instances of some subclass that multiply inherits both A and B. For example, instances of this C class are instances of A and instances of B. But not all intersection types need to involve multiple inheritance. We also have structural types in Python, like protocol or callable, which describe something about the shape of an object rather than describing its class. So you could imagine, for example, an intersection of A with a protocol like has foo, representing all instances. This intersection between these two would represent all instances of A that also have a foo method, maybe because some subclasses of A have that method. Of course, we might have two types with no overlap, where no object can possibly inhabit both types. For example, two final classes. Since you can't inherit them, you can't multiply inherit them, nothing can be both an F and a G. So in this case, we can say that these types are disjoint, and their intersection is equivalent to another important type, never. Never is the empty type. No Python object inhabits the type never. Another interesting intersection that is equivalent to never is the intersection of any type with its own negation. So T and not T for any type T is always never, since there can never be any overlap between a type and its negation. One more pair of useful corollaries for set-theoretic types. If we have two types where one is a subtype of the other, for example, a class that inherits another class, that means that all objects which are instances of child are also instances of base. So the combined area of those two types is the same as base itself. So the union of child and base is just base, and conversely, the overlap of these two circles is the same as child, so the intersection of child and base is simply child. So with that background in mind, we can come back now to this example, where the live binding with a narrowed constraint gives us this intersection type, int or none and not none. So in TY, we always represent internally union and intersection types in disjunctive normal form, or DNF. More simply put, this means we can have intersections inside unions, but never the other way around. This type is currently not in DNF. We have a union inside an intersection, so we'll simplify it. First, we distribute the intersection across the union. Then we observe that, as we just mentioned in the last slide, none and not none must simplify to never. Since never is the empty type, it can't contribute anything to a union, so it just disappears out of a union, so we can just remove that part. Now we can also notice that no integer can be none, which means that int is a subtype of not none. Every int is part of the type not none. So we can simplify this intersection to just int. So in the end, checking the return type of this function boils down to asking whether int is assignable to int, and of course it is. Let's look at one more example before we move on. Here we have an authenticated request class, which has user ID and email attributes. And then we have an anonymous request class, which has neither. And then a type alias for a union of those two types. So this combination of final classes and a union is one way to spell in Python a pattern that's often called sum types or algebraic data types. So we have a handle request function that takes in a request, and then it checks for a user ID attribute on the request. If it finds one, it knows we are dealing with an authenticated request, and it allows us to access also the email attribute without an error. Otherwise, we have an anonymous request. What's interesting about how TY handles this case is that there's no special casing of this. There's no union filtering or anything like that happening. This behavior entirely falls out from the general principles of intersection types. When we see this has-adder check, the narrowing constraint we generate is a synthetic protocol type with the user ID attribute. So for a use of request inside that block, we will initially construct the type, the intersection of request, the initial type of the request variable, and this synthetic protocol. The first step that we take in normalizing this type is to expand the type alias to its full union. Then, just as in the previous example, we'll distribute the intersection across the union. The second part of this union is the intersection of anonymous request and the synthetic protocol. But anonymous request does not have a user ID attribute, and it's final, which means this intersection is empty or simplifies to never, so it can just disappear from the union. It's important here that anonymous request is final. Otherwise, we'd have to consider the possibility that some unknown subclass of anonymous request might add a user ID attribute. And in that case, that would mean that the anonymous request type and the protocol would overlap, because there could be some instances of anonymous request that do have a user ID attribute. And if those types overlapped, then we couldn't eliminate the possibility that we're dealing with an anonymous request here. So it's important that it's final. Now, this remaining intersection of authenticated request and the synthetic protocol also simplifies. Every instance of authenticated request has a user ID attribute. That means that authenticated request is a subtype of this protocol, which means we can simplify this intersection to just authenticated request. In the else branch, we intersect with the negation of this synthetic protocol type. The simplification then follows the same pattern but in mirror image, and we end up with just anonymous request in that branch. Okay, before I wrap up, I want to touch on a surprisingly complex aspect of building a type checker, which is just emitting diagnostics. So say we've written this code, pretty straightforward. We inherit some base parser class and then define a parse method on our parser. Now we run TY and it gives us a diagnostic. Let's look at some of the components of this diagnostic. First, this is an error level diagnostic. It's not just a warning or info. Every diagnostic code in TY has a default severity level. You can also configure the severity level of each code. Second, we have the diagnostic code that you'd use to refer to this diagnostic in your configuration or in a suppression comment. And then third, we have a brief summary message describing what the problem is. Our parse method is overriding a parse method in the base parser class, and we're overriding it in an incompatible way. Then we show you exactly where in your code the problem is, which file, which line number, and a more detailed description of exactly what's wrong at that location. Then for many diagnostics, we'll also show you some related code that might be important to understand the issue. In this case, the error is an invalid override, so we show the base class method that you're overriding. This class, in this example, is located in a totally different module. It could even be in a third-party library or in TypeShed. Either way, we'll still point you directly to the relevant definition. In this case, it's already reasonably clear from comparing the override and the base method what the problem likely is, since we can see that our override has this extra slash in the signature, which makes all the arguments positional only. But TY also adds an additional message to clarify. The problem is that the data argument is positional only in the override, but the base method allows it to be passed as a keyword argument. So the override restricts further how it can be called, which means the subclass isn't safely substitutable for the base class, so that's a type error. Here's a more complex example. We have a text registry class attempting to implement a protocol registry, where each defines a register method that takes a callback, and then at the end, we try to assign a text registry to a variable typed as registry. If we run TY on this code, we'll get an error. The main error in the code frame here just tell us that a text registry isn't assignable to a registry, which is fine, but not very informative. We probably want to know why it isn't assignable. So TY also gives you this tree with the full nested details. Text registry is not assignable to registry because the register method on text registry isn't assignable to the method on the registry protocol. Why not? Because the callback type in the argument isn't assignable. Why not? Because text reader isn't assignable to the reader protocol. Why not? Because the read method isn't assignable. Why not? Because text reader.read returns a string, but reader.read returns bytes. So having your type checker proactively do a 5 whys analysis like this in complex failed type assignments can really save a ton of debugging and digging time. One potential issue with providing all this diagnostic context is that collecting it isn't free. The deeply nested assignability context that we just saw requires a fairly heavy tree-like data structure to collect. Providing context pointers like we saw to other files across the codebase introduces a salsa dependency directly to the exact source text of that file, which then will cause more invalidation on your next change. So it's very important that we are as lazy as possible about doing this extra work also. If there's additional context that we only need to emit a diagnostic, we need to not collect it until we've actually seen an error and we know we'll emit a diagnostic. So if the file is just a library dependency that we aren't actually checking and we aren't going to display diagnostics for, then we're not going to be displaying a diagnostic, so we should not be doing any extra work to collect diagnostic context. Also, if the specific diagnostic code is disabled in your configuration, or even if it's suppressed on that particular line with the type ignore comment, then we won't be displaying the diagnostic, and we need to not do this extra work to collect the extra context. So this requires careful design of our diagnostics API to make it hard for us to accidentally break these rules. Yeah. So here's what the usage of our diagnostics API looks like. So you don't have to fully understand this Rust code. The main point is this outer if condition here. We make it so that we have to ask for a diagnostics builder by first providing a diagnostic code and an AST node. And the diagnostic system won't even give us back a builder unless that diagnostic code is actually enabled for that specific location. Only once we have that builder object, which means we know we're going to be displaying this diagnostic, can we even start actually building the diagnostic up and attaching context to it and sub-diagnostics, et cetera. Another thing that's important is that we often prefer to redo some work in case of an error rather than making the fast path slower. For example, this tree-like assignability error context, as I mentioned, is fairly heavyweight to collect. We don't want to do that work on every assignability check up front, since most assignability checks in your codebase probably will not fail. So instead, we initially do the assignability check without the context. Then, if we have an error, and if we are going to display that error, we will redo the entire assignability check from scratch with context collection enabled this time in order to give us these details to show you. All right, we are almost done. Last thing is I want to very briefly talk about contributing to TY. TY is MIT licensed, developed fully in the open. We organize our roadmap and make decisions via GitHub. TY already incorporates excellent contributions from hundreds of external contributors. Probably many of you are already in that bunch, and if not, we would welcome your contributions. If you would like to learn more about TY or dig deeper into anything discussed in this talk, I'll be available after the talk, and right after lunch, we'll have an open space in room 202C, so come on by. Thank you.
Wow, thank you so much for that amazing talk, Carl. Let's give him some more appreciation for that amazing talk. We have exactly 7 minutes for questions, so please line up in front of the microphone for the ability to ask your questions.
Okay, hi. Great talk. I really appreciated the context of sort of how do you even approach building a type checker, especially one that is being as fancy as this and not doing like the full scan. The diagrams were particularly helpful, and I thought the synthetic protocol was a super cool trick. I have a bit of a bugbear when it comes to previously rough check and still with TY, and it is possibly unresolved reference.
Uh-oh.
Can you talk a little bit about where that fits into this talk? Yeah. I know that diagnostic is turned off by default, and that's the bugbear. Why is that?
Yeah, so I mean, possibly unresolved reference is tricky because to error on that and not have false positives requires an extremely high level of precision, which is very difficult or sometimes impossible. So like one example code pattern you could think of is a pattern where up at the top of a function we say if foo, and then we bind something to x, and x is otherwise unbound. And then we have a bunch more code outside the if, and then later on we have another if foo, and then we use x, right? And so, I mean, you could argue that's not a great pattern for humans to understand or reliably maintain, but that pattern does occur, and the code works fine. So it's arguably a false positive if we say possibly unresolved reference on x. And there are techniques for statically analyzing that pattern and kind of like mutating and splitting and merging the ASTs so that you can actually analyze that properly. But that's a lot of additional work that no Python type checker does, and we don't do either. And so it's those kinds of patterns that made us feel like the cost-benefit balance was not there to enable that diagnostic by default. But if you're okay with those sort of arguable false positives and you would rather rework that code into a different pattern instead, it's right there and you can turn it on, and we'll happily give you an error for possibly unresolved reference.
Is it fair to say that that's then the AST, like the breadth first numbering and things like that, trying to just keep that quick is what that boils down to?
I mean, yeah, maybe. I mean, it's just, it's more just that like in the grand scheme of things, of all the things that we have to do, which is a very, very long list, sure. There are things that are higher impact than that particular analysis. But, you know, maybe someday.
Thank you for humoring me.
Yep.
Again, great talk, thanks. Possibly off topic, and feel free to tell me it is. So I'm getting TY diagnostic errors on some Django models. Yeah. So the question is, am I doing something wrong, or is it just not fully supported yet?
Or you're probably not doing anything wrong. I mean, so this is a general problem for Python typing, right? Is that there are these libraries that have been around for a long time that use Python's metaprogramming and dynamic techniques in ways that are hard for type checkers to understand. So different type checkers take different approaches to this. Like MyPy has a plugin API, so there's a Django plugin, and then it understands this stuff. Some type checkers just sort of build in support for some of these patterns directly as a special case for Django specifically. That's something that we're evaluating. Okay. It looks like the Python type system may actually have sufficient expressiveness now to type most of what Django does using generic facilities available with the right stubs for Django. And there is someone currently working on developing some improved stubs for Django that take advantage of those more modern capabilities. And so we're kind of, there's big costs to having every type checker embed sort of an understanding of what Django does. Because anytime Django changes anything, you have to go change it in 4 different type checkers. And so we'd really love to see a set of Django stubs that make that unnecessary. So at the moment we're holding off and waiting to see how well that works. But we may end up having to do some special casing of Django.
Gotcha, thank you.
Yep.
Hi, great talk again. Oh, great talk again.
Thank you.
One of the things that's notable about a lot of the new type checkers like Firefly and TY, you probably get that as well, is that they add a lot of extra extension features to the typing system on top of what is in the standard PEPs. For example, intersection, not, type of, all these things in TY extensions. How do you see like your rationale when you, like what boundary do you add things? So for example, like conditional types or something might help with some of the situations came from earlier questions. And where do you see moving these into PEPs? Like what do you see the long-term story for these things? There's been some resistance in the past about adding intersection types to Python. What do you see the future of that?
Yeah, I mean, that's a very tricky question, and there's certainly a tension between innovation and trying new things that haven't been done before, and also aiming for some level of standardization and conformance between type checkers so that there's less frustration with trying to satisfy all of them if you're writing a library. And there aren't any easy answers to that tension. I don't think the Python type system is ready to be frozen in concrete yet, but we also do want to be thoughtful about. So I mean, I think to a certain extent, we're trying things in TY, some things that haven't been tried before, to see how they work and what in practice the pros and cons are. And we've already done some experiments that then we've later said, that doesn't look like a net win. It was theoretically interesting, it made some sense. In practice, it doesn't work well with the Python typing ecosystem, so we're gonna back off on that particular innovation. So that's a constant sort of evaluation that we're having to make. I think in terms of intersections specifically, there was a talk at the Typing Summit yesterday, and I think there is broad agreement that intersection types should be in the Python typing system because they're a very powerful primitive that is the natural complement of unions. And really, it's just a matter of that there's a lot of very tricky details to get right, and we don't want to do it. We don't want to get it wrong, and so it just takes a lot of work to get to an agreement about exactly what the details should look like.
Thank you.
Thanks for the talk. I had a question about the anonymous request example. In the branch, as you were going through, it was a has-adder check, but the member was statically defined, which you can analyze statically. But what if it was a variable, has-adder request, comma, why did I do this? You know, like, do you just not get the check?
It depends what the type of why did I do this is, right? So like, if the type that we have for why did I do this is a literal string type, meaning we can see where that type came from, either it's annotated as literal user ID, or we can actually see the assignment where user ID string was assigned to it, then we are confident that it is the string user ID and everything will work exactly as I showed. There's actually no difference in how we handle it. If the type that we have for that is just string and we don't know anything more, then obviously we can't draw any conclusions about what attribute it's checking for, so we can't do any of this.
I figured, I just was curious.
Yeah, makes sense.